In tackling this first set of problems, we're going to be graphing our enthalpy of combustion. We're going to do this in each section here, so I just wanted to show you what I really am looking for you in graphing this. On your x-axis is going to be your number of carbons, okay? So we're comparing carbon chains. We've got methane, ethane, propane, butane, so on and so forth. We're going up to a 10 long carbon chain. And then on the y-axis, you're graphing your enthalpy of combustion. This is going to be for the whole thing. Now I want to be very clear about that, because in our table, we're looking at comparing the enthalpy of combustion per CH2 and the total enthalpy of combustion. On the graph, we're looking at the total enthalpy of combustion, because what we want to be able to do is see how that slope changes as we increase our number of carbons, okay? In addition, as we're going through this whole assignment, I highly encourage you to get a ball and stick model and start making these structures so that you can physically see with your own eyes how these reactions would occur. So make the hydrocarbons that you're working with and make a little O2 molecule so you can kind of see. In order for this reaction to occur, this O2 has to be able to hit this hydrocarbon the right way, okay? In this assignment, we're going to be investigating a particularly useful attribute of hydrocarbons: their ability to be combusted in the presence of oxygen. This combustion reaction is well known to produce a lot of heat. In fact, we use it to heat our homes in any natural gas furnace. And if you have a wood-burning stove, really the wood is just acting in place of the hydrocarbon. It's a little more complex, but it's still reacting with oxygen to produce CO2 and H2O. In addition to creating those new molecules, it is releasing a lot of energy. When these molecules are broken up and reformed into CO2 and H2O, their stability increases. And so we can actually look at the amount of energy being released in that molecule to inform us of its stability. What we're going to look at the most in more specificity is how stable it is per set of molecules. So in this assignment, we're comparing these heats of combustion, also known as enthalpy of combustion, and we're going to be looking at the difference between each one. So the difference here would be 1561 minus 890, which gives me 671. I can look at the difference here, and I would get a similar number. We're going to keep looking at that difference as we go forward. So you'll need to actually calculate each of these. Then we're also asking, what's the number of CH2s? What does that really mean? Well, if I erase my reaction here, you can look at that very steadily. Notice CH4 here, I just have carbon attached to 4 hydrogens. There are no CH2s there, so 0. The next compound is ethane. Well, ethane is really just this attached to another carbon. Well, really that's 2 CH3s. So that's not going to have any CH2s. So hit a 0 there too. No worries. But what we're going to start to get is on our next carbon, with our next addition, we're going to have a CH2 in that middle section there. In fact, we could rewrite this formula to be CH3, CH2, CH3. If I wanted to add another one, going from propane to butane, I could write that as CH3. That's going to be my end carbon here. You see that? I've got a carbon attached to 3 hydrogens and then attached to the next thing, which is a CH2. And in butane, I'm going to have 2 of those. Then attached to a CH3. Looking just like that. So in propane, I've got 1, butane, I've got 2, and as I go up, I'm going to increase that number. I can generalize the formula of an alkane using the standardized form of CnH2n plus 2. So for every hydrocarbon, for every alkane, single bonds only, double bonds are going to futz with that a little bit. But for every single bond hydrocarbon chain, I can just take my number of carbons. So for example, let's go if I've got 15 carbons, I would have 15 carbons, and then how many hydrogens would I have? Well, I would just double 15, so 2N. That'd be 30, and add 2 more. So I'd have 32 hydrogens. And that should make sense because each middle carbon here is going to have 2 hydrogens, hence the 2N. The end carbons are both also going to have 2 hydrogens, still 2N, but they're also going to have 1 extra one on either end. So the ends of this hydrocarbon are going to have 2 extra hydrogens. That's how that works. So that's why we get this generalized form of CnH2n plus 2. So regardless of how long a hydrocarbon chain is, as long as there are only single bonds, I can figure out exactly how many carbons and hydrogens are going to be in that. And once I have that formula, I can easily figure out how many CH2 molecules will be in there by removing 2 carbons. My 2 end carbons will always be CH3. So if I've got something like C15H32 and I want to know how many of these CH2 molecules do I have, well, I really have CH3, a certain number of CH2s, and then a CH3, right? For every one of these, that's going to be the case. So how many CH2s do I have? Well, I used 2 of my carbons, started at 15, then I have 13 left. So for C15, I would have 13 CH2 molecules. Okay, that's going to be important because we're going to see a trend between the number of CH2s and the amount of energy that each one increases by. So go ahead and fill out that table, answer what questions you can, then come back for the second part of this video, and we'll go through that.